Time dependence of joins. The three types of joins described here, stream table, and table have a lot in common. They all require the stream processor to maintain some state search and click events, user profiles, or follower list based on one join input, and query that state on messages from the other join input. The order of the events that maintain the state is important. It matters whether you first follow and then unfollow, or the other way round. In a partitioned log, the ordering of events within a single partition is preserved, but there is typically no ordering guarantee across different streams or partitions. This raises a question. If events on different streams happen around a similar time, in which order are they processed? In the stream table join example, if a user updates their profile, which activity events are joined with the old profile processed before the profile update, and which are joined with the new profile processed after the profile update? Put another way, if state changes over time, and you join with some state, what point in time do you use for the join? Such time dependence can occur in many places. For example, if you sell things, you need to apply the right tax rate to invoices, which depends on the country or state, the type of product, and the date of sale, since tax rates change from time to time. When joining sales to a table of tax rates, you probably want to join with the tax rate at the time of the sale, which may be different from the current tax rate if you are reprocessing historical data. If the ordering of events across streams is undetermined, the join becomes non-deterministic, which means you cannot rerun the same job on the same input and necessarily get the same result. The events on the input streams may be interleaved in a different way when you run the job again. In data warehouses, this issue is known as a slowly changing dimension (SCD), and it is often addressed by using a unique identifier for a particular version of the joined record. For example, every time the tax rate changes, it is given a new identifier, and the invoice includes the identifier for the tax rate at the time of sale. This change makes the join deterministic, but has the consequence that log compaction is not possible, since all versions of the records in the table need to be retained. Fault tolerance. In the final section of this chapter, let's consider how stream processors can tolerate faults. We saw in Chapter 10 that batch processing frameworks can tolerate faults fairly easily. If a task in a MapReduce job fails, it can simply be started again on another machine, and the output of the failed task is discarded. This transparent retry is possible because input files are immutable. Each task writes its output to a separate file on HDFS, and output is only made visible when a task completes successfully. In particular, the batch approach to fault tolerance ensures that the output of the batch job is the same as if nothing had gone wrong, even if in fact some tasks did fail. It appears as though every input record was processed exactly once, no records are skipped, and none are processed twice. Although restarting tasks means that records may in fact be processed multiple times, the visible effect in the output is as if they had only been processed once. This principle is known as exactly once semantics, although effectively once would be a more descriptive term. The same issue of fault tolerance arises in stream processing, but it is less straightforward to handle. Waiting until a task is finished before making its output visible is not an option, because a stream is infinite and so you can never finish processing it. One solution is to break the stream into small blocks, and treat each block like a miniature batch process. This approach is called microbatching, and it is used in Spark streaming. The batch size is typically around 1 second, which is the result of a performance compromise. Smaller batches incur greater scheduling and coordination overhead, while larger batches mean a longer delay before results of the stream processor become visible. Microbatching also implicitly provides a tumbling window equal to the batch size windowed by processing time, not event timestamps. Any jobs that require larger windows need to explicitly carry over state from one microbatch to the next. A variant approach, used in Apache Flink, is to periodically generate rolling checkpoints of state and write them to durable storage. If a stream operator crashes, it can restart from its most recent checkpoint and discard any output generated between the last checkpoint and the crash. The checkpoints are triggered by barriers in the message stream, similar to the boundaries between microbatches, but without forcing a particular window size. Within the confines of the stream processing framework, the microbatching and checkpointing approaches provide the same exactly once semantics as batch processing. However, as soon as output leaves the stream processor, for example, by writing to a database, sending messages to an external message broker, or sending emails, the framework is no longer able to discard the output of a failed batch. In this case, restarting a failed task causes the external side effect to happen twice, and microbatching or checkpointing alone is not sufficient to prevent this problem. In order to give the appearance of exactly once processing in the presence of faults, we need to ensure that all outputs and side effects of processing an event take effect if and only if the processing is successful. Those effects include any messages sent to downstream operators or external messaging systems including email or push notifications, any database writes, any changes to operator state, and any acknowledgement of input messages including moving the consumer offset forward in a log-based message broker. Those things either all need to happen atomically, or none of them must happen, but they should not go out of sync with each other. If this approach sounds familiar, it is because we discussed it in Exactly Once Message Processing on page 360 in the context of distributed transactions and two-phase commit. In Chapter 9 we discussed the problems in the traditional implementations of distributed transactions, such as XA. However, in more restricted environments it is possible to implement such an atomic commit facility efficiently. This approach is used in Google Cloud Dataflow and VoltDB, and there are plans to add similar features to Apache Kafka. Unlike XA, these implementations do not attempt to provide transactions across heterogeneous technologies, but instead keep them internal by managing both state changes and messaging within the stream processing framework. The overhead of the transaction protocol can be amortized by processing several input messages within a single transaction. Our goal is to discard the partial output of any failed tasks, so that they can be safely retried without taking effect twice. Distributed transactions are one way of achieving that goal, but another way is to rely on idempotence. An idempotent operation is one that you can perform multiple times, and it has the same effect as if you performed it only once. For example, setting a key and a key value stored to some fixed value is idempotent. Writing the value again simply overwrites the value with an identical value, whereas incrementing a counter is not idempotent. Performing the increment again means the value is incremented twice. Even if an operation is not naturally idempotent, it can often be made idempotent with a bit of extra metadata. For example, when consuming messages from Kafka, every message has a persistent, monotonically increasing offset. When writing a value to an external database, you can include the offset of the message that triggered the last write with the value. Thus, you can tell whether an update has already been applied, and avoid performing the same update again. The state handling in Storm's Trident is based on a similar idea. Relying on idempotence implies several assumptions. Restarting a failed task must replay the same messages in the same order. A log-based message broker does this. The processing must be deterministic, and no other node may concurrently update the same value. When failing over from one processing node to another, fencing may be required. See the leader and the lock on page 301 to prevent interference from a node that is thought to be dead, but is actually alive. Despite all those caveats, idempotent operations can be an effective way of achieving exactly once semantics with only a small overhead. Any stream process that requires state, for example, any windowed aggregation such as counters, averages, and histograms, and any tables and indexes used for joins must ensure that the state can be recovered after a failure. One option is to keep the state in a remote data store and replicate it, although having to query a remote database for each individual message can be slow, as discussed in Streamed Table Join Stream Enrichment on page 473. An alternative is to keep state local to the stream processor and replicate it periodically. Then, when the stream processor is recovering from a failure, the new task can read the replicated state and resume processing without data loss. For example, Flink periodically captures snapshots of operator's state and writes them to durable storage such as HDFS. Samza and Kafka streams replicate state changes by sending them to a dedicated Kafka topic with log compaction, similar to change data capture. VoltDB replicates state by redundantly processing each input message on several nodes. See actual serial execution on page 252. In some cases, it may not even be necessary to replicate the state, because it can be rebuilt from the input streams. For example, if the state consists of aggregations over a fairly short window, it may be fast enough to simply replay the input events corresponding to that window. If the state is a local replica of a database, maintained by change data capture, the database can also be rebuilt from the log-compacted change stream. See log compaction on page 456. However, all of these trade-offs depend on the performance characteristics of the underlying infrastructure. In some systems, network delay may be lower than disk access latency, and network bandwidth may be comparable to disk bandwidth. There is no universally ideal trade-off for all situations, and the merits of local versus remote state may also shift as storage and networking technologies evolve. Summary. In this chapter we have discussed event streams, what purposes they serve, and how to process them. In some ways, stream processing is very much like the batch processing we discussed in Chapter 10, but done continuously on unbounded never-ending streams rather than on a fixed size input. From this perspective, message brokers and event logs serve as the streaming equivalent of a file system. We spent some time comparing two types of message brokers. ANCP/JMS style message broker. The broker assigns individual messages to consumers, and consumers acknowledge individual messages when they have been successfully processed. Messages are deleted from the broker once they have been acknowledged. This approach is appropriate as an asynchronous form of RPC. See also message passing data flow on page 136, for example in a task queue, where the exact order of message processing is not important and where there is no need to go back and read old messages again after they have been processed. Log-based message broker. The broker assigns all messages in a partition to the same consumer node and always delivers messages in the same order. Parallelism is achieved through partitioning, and consumers track their progress by checkpointing the offset of the last message they have processed. The broker retains messages on disk, so it is possible to jump back and reread old messages if necessary. The log-based approach has similarities to the replication logs found in databases. See Chapter 5 and log structured storage engines. See Chapter 3. We saw that this approach is especially appropriate for stream processing systems that consume input streams and generate derived state or derived output streams. In terms of where streams come from, we discussed several possibilities: user activity events, sensors providing periodic readings, and data feeds. For example, market data in finance are naturally represented as streams. We saw that it can also be useful to think of the writes to a database as a stream. We can capture the changelog, i.e. the history of all changes made to a database, either implicitly through change data capture or explicitly through event sourcing. Log compaction allows the stream to retain a full copy of the contents of a database. Representing databases as streams opens up powerful opportunities for integrating systems. You can keep derived data systems such as search indexes, caches, and analytic systems continually up to date by consuming the log of changes and applying them to the derived system. You can even build fresh views onto existing data by starting from scratch and consuming the log of changes from the beginning all the way to the present. The facilities for maintaining state as streams and replaying messages are also the basis for the techniques that enable stream joins and fault tolerance in various stream processing frameworks. We discussed several purposes of stream processing, including searching for event patterns, complex event processing, computing windowed aggregations, stream analytics, and keeping derived data systems up to date. Materialized views. We then discussed the difficulties of reasoning about time in a stream processor, including the distinction between processing time and event timestamps, and the problem of dealing with straggler events that arrive after you thought your window was complete. We distinguished three types of joins that may appear in stream processes. Stream joins. Both input streams consist of activity events, and the join operator searches for related events that occur within some window of time. For example, it may match two actions taken by the same user within 30 minutes of each other. The two join inputs may in fact be the same stream. A self-join if you want to find related events within that one stream. Stream table joins. One input stream consists of activity events, while the other is a database changelog. The changelog keeps a local copy of the database up to date. For each activity event, the join operator queries the database and outputs an enriched activity event. Finally, we discussed techniques for achieving fault tolerance and exactly once semantics in a stream processor. As with batch processing, we need to discard the partial output of any failed tasks. However, since a stream process is long-running and produces output continuously, we can't simply discard all output. Instead, a finer-grained recovery mechanism can be used, based on microbatching, checkpointing, transactions, or idempotent writes. Ian Malpass. Measure anything, measure everything. Codesgraph.com, February 15, 2011. Jim N. Gray. Queues or databases. Microsoft Research Technical Report MSRTR 95-56, December 1995. Sanjay Agari, Matthew Arat, Mark Atwell, et al. AMCP. Advanced Message Queuing Protocol Specification, version 0-9-1, November 2008. Google Cloud Pub/Sub, a Google Scale Messaging Service, cloud.google.com, 2016. J. Krebs, Nanarked, and John Rao, Kafka, a distributed messaging system for log processing, at 6th International Workshop on Networking Meets Databases NetDB, June 2011. Yogeshwar Sharma, Philippe Adjou, Pechenang, et al. Wormhole. Reliable PubSub to support geo-replicated Internet services at 12th Usenix Symposium on Networked Systems Design and Implementation in SDI, May 2015. P.S. Narayan, Sherpa Update, developer.yahoo.com, June 8. Dan Harvey, Change Data Capture with Mongo plus Kafka at Hadoop Users Group UK, August 2015. Oracle Golden Gate 12c, Real-Time Access to Real-Time Information, Oracle White Paper, March 2015. Apache CouchDB 1.6 Documentation, docs.couchdb.org, 2014. Greg Young, CQRS and Event Sourcing at Code on the Beach, August 2014. Martin Kleppmann, Making Sense of Stream Processing, Report, O'Reilly Media, May 2016. Sander Mack, Event Source Architectures with Akka, at Java 1, September 2014. Julian Hyde, Personal Communication, June 2016. Datomic Development Resources, Excision, Cognitect, Inc. docs.datomic.com. Fossil Documentation, Deleting Content from Fossil, fossilscm.org, 2016. Philippe Flageolet, Eric Fossey, Olivier Gandallet, and Frédéric Munier. Hyperlog Log, The Analysis of a Near-Optimal Cardinality Estimation Algorithm, at Conference on Analysis of Algorithms AALPHA, June 2007. Shay Bannon, Percolator, Elastic.co, February 8, 2011. Stephen Ewan, Streaming Analytics with Apache Flink, at Kafka Summit, April 2016. Ryan Betts and John Hugg, Fast Data, Smart and at Scale, Report, O'Reilly Media, October 2015. Flavio Junqueira, Making Sense of Exactly One Semantics, at Strata Plus Hadoop World London, June 2016. J. Krebs, Trying to Achieve Deterministic Behavior on Recovery/Rewind, email to Samzadev mailing list, September 9, 2014.